The following is an original production of AZPM News.
For Arizona Public Media, I'm Erika Hamden, professor of astrophysics at the University of Arizona, and this is Arizona Science. Joining me today is Ramya Anche, assistant research professor of astronomy at the University of Arizona. Ramya's research focuses on polarized light in a range of circumstances in the universe. She's also worked on both the largest ground-based telescopes and now is starting work on a small satellite that will launch in a few years called PUFFINS. Welcome, Ramya.
Thank you so much.
So first, before we get to PUFFINS, I was hoping that you could explain to our listeners what polarized light is and why it's useful for observing the universe.
Polarization is very much part of our daily life, starting from polarized sunglasses to mobile phones or the computer monitors we use, they all emit polarized light. Like if you look at polarized sunglasses, when you're looking at glare from water surfaces or snow or ice, what happens is the reflected light is polarized and in a one particular direction.
By the reflection.
Yeah, but when you wear your sunglasses, it is orthogonal to the direction of the vibration and it blocks all this polarized light from the glare. So that's why you see a lot of difference between when you wear polarized sunglasses and look at ice or water and with compared to your normal sunglasses.
So how is polarization important in observations of like the universe or our galaxy?
Polarization is a phenomenon which we observe in most of our astrophysical sources, starting from even stars or interstellar dust or even exoplanets and exoplanetary systems. In the case of stars, especially in terms of like when the end of the star life where there is supernova or nova explosion, we see polarization. And it helps us understand what kind of symmetry or asymmetry which is present in these explosions. In the case of exoplanetary systems like asteroid belt, analogs in those systems, they have mostly these dust grains or rocky bodies which also emit polarization by scattering. So polarization helps us understand starting from asymmetry and magnetic fields in our interstellar dust to understanding composition in the exoplanetary system. It gives us the missing piece of information which we don't get with just imaging or just by understanding a spectra. It provides us another information which cannot be obtained by any other technique.
You recently had a mission concept selected. You're the PI. This is a mission funded by NASA called PUFFINS. So can you tell us a little bit about PUFFINS and what it's going to help us understand?
PUFFINS stand for polarimetry in ultraviolet to find features in interstellar dust. So we are trying to understand polarization from these interstellar dust grains in our universe. And we are measuring these polarization signals in ultraviolet wavelengths. And it helps us understand the composition of interstellar dust grains and their distribution in our galaxy.
And so an interstellar dust grains is just like little particles that are kind of in between stars within our own galaxy. So how does the composition kind of matter? Why is that important to figure out?
The interesting thing about interstellar dust is although it occupies only like 1% of visible mass in Milky Way, it helps us understand stellar evolution, galaxy evolution, and also composition, basically how it is varying across the universe.
So how is PUFFINS going to help us to kind of understand this dust?
The one area where PUFFINS is really unique is understanding smaller grain dust sizes because these smaller dust grain sizes were not explored for the last 30 years. The last dedicated UV spectropolarimetry mission happened in 1995.
Okay.
So if we want to go look at smaller dust grains, then we have to go make observations in ultraviolet wavelengths. So using PUFFINS, will be able to understand dust grains of size of 50 nanometers, which is like a scale of common cold virus.
Oh, so very tiny.
Yeah. And at the same time, in tandem, when we are doing these dust grain measurements using PUFFINS, we are also going to do observations using the ground-based telescopes in optical and near-infrared wavelengths, where you can actually understand smaller dust grains to the largest dust grains which are possible, which gives us kind of distribution of these dust grains at different parts of the sky.
So what are you most excited for about this project that is just beginning?
Oh, I'm very excited that I'm able to do this from start to end, like starting from the design process, and we are putting the science cases together, we're putting the requirements together, and then building it and testing it in the lab, and then finally being able to launch in very short period of time.
So when are you targeting for a launch?
We are potentially targeting 2030 because we are just getting started. So it's 4 years to launch.
Which for space missions is very short.
Yes, because astrophysics pioneers are designed in a way it's like low cost, fast paced missions. And we don't do a lot of technology development in this. We put in like the optics or all the components which are already space qualified.
There is another NASA telescope which is launching later this year at the end of August. It's called the Roman Space Telescope. And I understand that you also have done some polarimetry work for them. Can you tell us about that?
The Roman Space Telescope, which is going to be launched at the end of August, has a coronagraph instrument where we suppress the starlight in order to directly image the exoplanet. And this coronagraph instrument also has a polarimetry mode where we can go and we can observe the polarized signals either from exoplanets or from these dusty asteroid or Kuiper belts which are present in other planetary system. So I've been working with Roman Space Telescope for the last 4 years, trying to come up with these observation proposals like what targets we're going to observe in polarized mode to understand polarized signals from these asteroid or Kuiper belts. So currently we are doing the observation phase.
So when the telescope launches, we'll be able to understand how similar some of these asteroid belts, Kuiper belts, are to the composition of our own asteroid belt or Kuiper belt. And then that gives us a little more detail into kind of the origins of those planetary systems and maybe why they have the architectures that they have, the number of planets and the composition.
Yeah, exactly. They help us understand where rocky planets could form or where ice giants could form. So it's only by polarimetry we understand the composition.
How did you get interested in this work when you were starting out in your career?
I was always interested in astronomy right from my undergrad. I started my grad school in astronomical instrumentation, and I was more interested in adaptive optics, but then moved to polarimetry because I liked a lot of math, and I also liked working with Wollaston's, which are like the basic optical component, which gives you polarized light. So that's how I got interested, and for the last 10 years, I've been working on polarimetry.
You worked on polarimetry for ground-based telescopes, like one that is in development called the Giant Magellan Telescope, which is a 28-meter primary mirror that's going to get built in South America. So tell us about your work on that.
During my grad school, I started with a 30-meter telescope, which is another US ELT, and design a polarimeter, but it did not materialize completely. And then when I moved to University of Arizona, because U of A is a partner in GMT, that's when I thought that, okay, it'll be really cool to have a polarimeter on GMT. So I'm currently working with another faculty at U of A to design a polarimeter for Giant Magellan Telescope. So it's going to happen after PUFFINS or in parallel with PUFFINS.
Thanks so much for talking with us, Ramya. It's going to be really exciting to see how PUFFINS changes our understanding of how planetary systems form from the smallest dust grains up to, what happens to a planet.
Thank you so much for having me.
This is Erika Hamden, and you've been listening to Arizona Science. We've been talking with Ramya Anche, who is the PI of a new NASA telescope called PUFFINS, being built at the University of Arizona. You can hear more of this conversation and others on our Arizona Science segments by going to azpm.org/Arizona Science.
This has been an original production of AZPM News.